Hello, my lovely students. Welcome once again to Dr. Saras's classes. We were doing our group theory part, and we have completed a lot on group theory with a lot of mathematical examples, with a lot of definitions, with a lot of important points, and a lot has been covered in group theory. So, we are still continuing on that. There is a lot more left on group theory to do. Okay, so let's not lose our excitement here, and let's keep that force and power of studying, and let us continue with the next part of group theory. So in this part of group theory, as you can already see on your screen, on your mobile screen, on your computer screen, wherever you would like to watch this video, you can watch this video. Okay, so you look at your computer screen. Today topic is going to be some important results on normal subgroups. If you remember, in the previous video I taught you what is a normal subgroup. I would like to go back to the previous slide where I had scribbled a lot there. It looks very, very beautiful here. Normal subgroup, a subgroup H of a group G is said to be normal subgroup if and only if HA is equals to AH for all A belonging to G. Okay, now we are moving on to our next part. So in this part, students, what we are going to do is clearly here on your screen. We are going to learn about some important results on normal subgroups. Okay, some important points on normal subgroups that will make a subgroup normal. First one, a subgroup of a group G is normal if G inverse H into G belongs to H. Now I would like to write that. So a subgroup H is a subgroup of a group G. Alright. Now H is normal only when this happens. G inverse HG will belong to the group H, subgroup H. Okay, for all H belonging to H and G belonging to the group G. So we will pick up two elements, one element H from the subgroup and one element G from the group, and then we will apply this type of a rule to check, this type of a way to check whether it belongs to that H group. Like if I give you an example with number, let's say I take a number 2, okay, from the group, and if I take a number say 3 from H, such that 3 belongs to H and 2 belongs to G. So if I do like this, 2 inverse into 3 into 2, then what do I get? This and this gone away. This is equal to 3. That belongs to H, right? Then it is a subgroup. That is the normal subgroup. Okay, this is a normal. It's a group is normal. The subgroup is normal. Okay, if this happens, let's move on to the second part. If H and K are two subgroups of G such that either H or K is normal in G, then H into K is a subgroup of G. It's a little different. Okay, it says that if H and K are two subgroups of G such that H or K is normal, H or any one of them K is normal in G, of course in G, then HK is a subgroup, SG I'm writing, in G. Okay, that will happen. This one finished, this one finished. Let's move on to the next one. If H is normal in G and K is a subgroup of G, then the intersection of H and K is normal in K. Okay, what does it say? It says if H is normal in G, that means H is a normal subgroup in G and K is a subgroup of G. K is just a subgroup but normal, not normal. Okay, H is normal but K is just a subgroup of G, then H intersection K is normal in K. H intersection K is normal in K. Alright, H intersection K is normal in K. The down part is getting rubbed off. Let's just put the thing, highlight. Then H intersection K is normal in only K. Okay, make sure you know that, understand. Moving on to our next one. If A is a subset of B and B is a subset of C, okay, B is a subset of G, sorry, A is a subset of B and B is a subset of G, A is normal in G and A is normal in B, then A is normal. If A is normal in G, then oh no, then A is normal in B also. Okay, that's what it says. Very simple, very simple. These ones are very, very, very simple. Very simple, very simple, very simple, very simple. Okay, let's move on to the sixth one. What does the sixth one say? Every subgroup of an abelian group is normal. Every subgroup of an abelian group is normal. You want to mark that point as important, very, very important point. I want you to mark this point important. I'm marking it with a red. What does it say? It says every subgroup of an abelian group is normal. Understood? Okay. Moving on to the seventh point. A subgroup of index 2 in a group of G is a normal subgroup of G. Another important one. Okay, what does it say? Let's rub off a little bit from here. Rubber, eraser. Come on, get erased. Get erased quickly. What happened? Why are these not getting erased? But no problem. Okay, this is what happened. That's why it's not getting erased, but will get erased. Okay, just hold on. Let me erase this. I need some space over here to write. They could have left some space, but anyways, not a problem. It's just a simple thing. Okay, it says that a subgroup of index 2. You have a subgroup SG. Let's say H. Okay, it has an index 2. If it has an index equal to 2, then G is index 2. A subgroup G, a subgroup of index 2 in a group G is normal. Okay, then H is normal in G because it has an index 2. Okay, that's why it is normal in G. Moving on to our eighth point. What is our eighth point saying? Our eighth point is saying that FP, let me rub that off. It says FP prime, okay, is the smallest prime factor of order of a finite group G. So this is the smallest prime factor. Smallest prime factor. This is the smallest prime factor of order of a finite group G. Of smallest prime factor of order of a finite group G, then any subgroup of index P is normal. So any subgroup of index P is normal. Yeah, provided that FP is the smallest prime factor of the order of a group. Okay, of a finite group. Okay, cannot be an infinite group, not possible. Okay, Moving on to our ninth point here. What is our ninth point? Let's mark the ninth point. Every finite group of even order has at least one element of order 2. Okay. Very interesting point. It says every finite group of even order. Every finite group of even order. Okay. You have a finite group and it's of even order. So order of the group is an even number. Like say 2, 4, 6, any even number. Okay. So if you have any even number, okay, in the order of the group, every finite group of even order has at least one element of order 2. It will have at least one element of order 2. That means order of the element will be 2. One element, only one. At least one, not only one, at least one. At least, emphasize on the word at least. At least one will be of the order 2. Moving on to our 10th point, students. If H is a normal subgroup of a group G of order 2, then H is a subset of Z. So it is saying that if H is a normal subgroup, let's rub this part off now. So if H is a normal subgroup, students, right? You have a normal subgroup H. NSG, normal subgroup. So if H is a normal subgroup of G, of the group G, of group G of order 2, order equal to 2, then H is an H is a subset of Z. Okay. Let's move on to our next point, 11th point. If H is a subgroup of G and X square, let's see what is that. I should not have X square. Yes, a X square belongs to H. For every X belong to G, then H is a normal subgroup of G. You might want to mark this as important as well. So what does it say? If H is a subgroup of G, okay, such that X square belongs to G, then H is a normal subgroup of G. Okay, moving on to the point number 12. Moving on to point number 12, let's get rid of whatever is written here. Okay, now in point number 12, if you go ahead and read point number 12 here, what does point number 12 say? Point number 12 says, if H and K are two normal subgroups, H and K are NSG, means normal sub. Okay, they are two normal subgroups of who? Of G as a group, GR. Okay, and only identity in intersection. If it only has when you do the intersection of H and K, you will get only the identity element. Okay, then HK is equal to KH for all H belonging to H and small k belonging to K. So when you have H and K as normal subgroups of G, and H intersection K becomes an identity. Okay, in their intersection you will get an identity. then HK will be equals to KH. Then this condition will be satisfied. You want to mark this condition with a highlighter or something red. Okay, it's too important that this condition is necessary. So what does it mean? Means if H and K are two normal subgroups of a group G, and when you do the intersection of them and you get the answer as the identity element, then this criteria is satisfied, such that the small h belongs to the capital H set and the small k belongs to the capital K set. Okay, moving on to our next point, students. For last point actually, for a group G, G and E are always normal subgroups of G. What does the identity element? G and just an E, a set with the identity E, they are always, these two are always normal subgroups. Always normal subgroups of G. Okay, and these subgroups are called trivial subgroups. Okay, there is a printing mistake here. I would like to just remove this word and I write it trivial. That is the correct spelling, students. Trivial. So these two types of groups are called trivial subgroups. Trivial subgroups of G. Okay, so another different type of name is given to the normal when this happens, that G for a group G, G and E are always normal subgroups. Then they are called trivial subgroups of G. So students, that's it for this part of the video. We have done many points with mathematical examples. Okay, and we shall continue this in the next video. So you keep taking as much help as possible from Dr. Saurav Sir's classes, because all the help that you will be needing will be provided here at Saurav Sir's classes. Thank you for watching, students. See you in the next video.